So here we give some examples. One is aluminum oxide, a very common ceramic material, colloidal suspension in water. I'm showing what? Zeta potential measured versus pH. Okay, it shows kind of this behavior. And the zeta potential is 0 means that have very little charge on the surface. Okay. Zeta potential becomes more positive when pH what? This is close to 7, 8. When pH decreases, zeta potential become more positive. Make sense? The pH decreases means the solution has more and more what? Proton. And proton attached to the surface make the zeta potential positive. On the other hand, it becomes more negative when pH increases. Because as you increase from neutral pH 7 to like 10, 12, there's more hydroxy group in the solution, negative ion, and when they are high, they attach to the surface, make the surface the potential negative. Make sense? Okay. And then here we are plotting zeta potential still against what? pH. But now we would have different concentration of so-called support electrolyte. Potassium nitrate. Potassium nitrate. People add different concentration of potassium nitrate for different pH. So for each of these curves, let's look at the circle. They represent what? Potassium nitrate at a concentration of 10 to the minus 4 molar. Okay, and then for this one, still as what we observed or what we would think, the lower the pH, the more positive zeta potential, the higher the pH, the more negative the zeta potential. And at 0, at certain pH value of PZC, point of zero charge, I have what? Negligible zeta potential or zero zeta potential. But at the same time, you would see for the same pH, let's say for the same pH of around 6, the zeta potential are all what? Positive. But as you see, as we increase in what? Electrolyte concentration, the absolute pH zeta potential become what? As we increase from 10 circle 10 to the minus 4 to 10 to the minus 2, increase in electrolyte concentration, supporting electrolyte concentration, our ionic strength, my zeta potential actually becomes less. Okay, which is very important. As the solution ionic strength goes higher and higher, means okay, the charge becomes higher or more concentrated electrolyte, my zeta potential becomes smaller, which means when you add too much electrolyte, your particle has a tendency to what? To compact, to agglomerate. Similarly, on the other side, at pH 10, from circle to square, I'm increasing what? From circle to square, I'm increasing electrolyte concentration at pH 10. At the same time, my zeta potential become absolute value become smaller. Make sense? Which means I have a greater tendency to agglomerate coming together. Okay. Let's look at another example, which is titanium dioxide colloidal suspension in water. In water, because that's the most common solvent, cheapest one. Okay. Here we are showing still what? Zeta potential against pH. Okay. Zeta potential is 0, means okay, highly agglomerated. And then we have different what? Supporting electrolyte concentration. But generally still, as we mentioned, the pH become lower, the zeta potential become what? More and more positive. Let's don't try not to use higher. More and more positive. On the other hand, when pH become higher and higher, the zeta potential become more and more negative. Makes sense? And here is 0. Okay, so that's the same trend that we said here. On the other side, for ionic strengths, answering from square to circle, from circle to square, we increase what? From concentration from circle to square, increase concentration, supporting electrolyte concentration, which means increasing ionic strength and decreasing what? Zeta potential. In this case, I'm still using potassium nitrate as my so-called supporting electrolyte. Okay, this plot shows still TiO2 against pH, but with a different electrolyte, sodium iodide. The trend is still similar. Low pH, positive zeta potential, high pH, negative zeta potential, but then from circle to square, we have increase in electrolyte concentration, and for the same pH, I have a decrease in absolute value. Make sense? From circle to square. From circle to square, I have a decrease in absolute value of the zeta potential, which means you do not want, if you want a stable suspension, you do not want to put too much supporting electrolyte in there. Make sense? You do not want to put too much supporting electrolyte in there. Okay? And then a third example, aluminum oxide suspension, but it is with so-called added sodium citrate, a electrolyte, and it shows zeta potential against sodium citrate concentration. Here we are not dealing with pH, aluminum oxide, but sodium citrate concentration. What we see is in the very beginning, as we increase the sodium citrate concentration, the zeta potential becomes what? Decrease, become much more negative. From 0, decrease rapidly, okay, from a very high negative value. Very high negative value. It means, okay, the citrate group, the citrate ion, as we get more and more, it is preferentially absorbed onto the aluminum oxide surface and give it a negative zeta potential. Okay, initially, zeta potential become more negative as more citrate ion absorb. From here to where? To here. But then, as we keep increasing the sodium citrate concentration, what is going to happen? The zeta potential absolute value what? Decrease, or it become more positive again because the so-called what? Ionic strength. You have too high concentration, you have too high ionic strength, and that is going to decrease the so-called the balance. Too high ionic strength is going to squeeze the electrical double layer, and that effectively decrease your zeta potential, which means you do not want to add too much sodium citrate in order to stabilize what? Aluminum oxide. A little bit. If you overdo it, you lose the benefit. Make sense? That's actually for all materials, that's this kind of sweet spot if for anything. You do add some, you develop a surface charge, make them stable, but you overdo it, start to decrease again. Okay, and this is holds true for all three different what? Loading, solid loading. VO means volume percentage, volume percentage. Okay, so let's talk about another example, which is silver iodide. Silver iodide, colloidal suspension in water. Again, I'm showing on the left mobility, mobility versus PAG means the negative decimal logarithm of silver ion. Negative decimal logarithm of silver ion. Take silver ion concentration, take the logarithm of the concentration, and take the negative. Like pH means the negative decimal logarithm of what? pH, H, proton. Okay. So the other one is zeta potential against PAG. Okay. So essentially what we see is at certain PAG, our zeta potential is what? 0. And when zeta potential is 0, it has very low also what? Mobility. Zeta potential is 0, it doesn't move very fast. Make sense? Why zeta potential is 0? It has very low mobility. Because mobility, you need what? Electrical field. In order for it to move within electrical field, it has to be charged. If it's charge neutral, you put electrical field there, does it move? If it's charge neutral, 0 zeta potential means you are almost close to charge neutral. Charge neutral, you put electrical field, does it move? It doesn't move. So that's why it got very low what? Mobility. Make sense? And then, as we go to first, PAG greater than this PZC, point of zero charge, greater, which means PAG is much higher than this value. PAG is much higher than this point of zero charge. Again, PAG much greater than 5. Remember, PAG much greater than 5 means the solution has what? Low concentration of silver. Just like high pH value means the solution has very little what? High pH means the solution has very low what? Proton, right? High pH is 12 means the solution has very low proton. This high PAG means the solution has very low what? Ag. It's the same. Okay. The solution has very low silver, and you have silver iodide means okay. The solution has very low silver. The silver iodide will have a preferential dissolution of silver. Make sense? The solution has very little silver. Then for this silver iodide, it has a tendency to give out silver. And because of this, it would have remaining what? Iodine ion attached to the surface. Here, the solution has very little silver ion. So to compensate, the particle has to give out what? Silver. And if the particle preferentially give out silver, the particle surface has remaining richer iodine, and remaining richer iodine is negatively charged. That's why it's got negative what? Potential, zeta potential. Okay, but it's here, it's going to be stable. On the other hand, when PAG is much smaller than 5, PAG is much smaller than 5, okay, PAG is much smaller than 5 means the solution has a lot of what? Silver. Just like pH is much smaller than 7 means the solution has a lot of proton. This one we have a lot of silver ion. And if the solution has a lot of silver ion in it, okay, in this case, my silver iodide does not want to give out more silver because the solution doesn't need it. The solution already has a lot of silver. It doesn't need the silver, actual silver. And in this case, the silver iodide, believe it or not, it wants to give out extra iodine ion. It wants to give out the iodine ion. And as a result, this silver iodide particle will have richer remaining positive charge. That's why it's got a positive zeta potential. Make sense? Okay? That's how we kind of understand